Hello, everyone. Well, thanks for having me on the stage. Today I'm going to talk about how deep learning can be used into fault injection attacks and, to be more precise, deep learning attribution methods. But before starting my presentation, I would like to know how, if you are familiar with this kind of attacks, I mean hardware attacks, fault injection side channel. If you are familiar with this, you can raise. Sorry. Oh, thank you. So I would like to know if you are familiar with this kind of attack, so you can raise your hand if you did this before. Okay, great. So a little bit about me. So my name is Karim, and I work as a hardware security expert at Ledger. Ledger is a hardware wallet vendor. So we are selling hardware wallets for self-custody for to store Bitcoin and cryptocurrencies. And more precisely, I work at the Ledger security research team, which is called Dungeon. So our daily work is to do offensive hardware security research on our products and also the products of our competitors. A little bit introduction about hardware attacks. So hardware attacks are divided into two categories, actually. The first category is fault injection attack, and the main idea of this kind of attacks actually is to perturb the chip during the execution of sensitive operations. You can imagine that you are executing a secure boot or pin verification. And the main idea of fault injection is to perturb this kind of operations, to skip, for example, the secure boot or pin verification, or also you can perturb the chip during the execution of crypto accelerators like EES or RSA and use statistical techniques, for example, like differential fault analysis to attack the key. How you can do that? You can do that using power and clock glitches, for example, or you can use electromagnetic fault injection, body biasing injection, or, for example, laser fault injection. The second category is related to side channel attacks, and it's completely different from fault injection attacks. Side channel are called like passive attacks, and we don't perturb the chip actually. We try to listen to what happens inside the chip by measuring the information that the chip leak actually. You can do that by measuring the timing, the power consumption, or the electromagnetic emissions of the chip. And we use some statistical techniques to perform this kind of attacks like differential power analysis, correlation power analysis, profiling attacks using deep learning for sure. Why I'm here today? So the motivation actually is more related to fault injection attacks. And I don't know if you have tried before to perform this kind of attacks in what I can call in black box mode. I mean, you attack a design that in a black box, you don't know any information about what happens in the chip. You just run the command and you don't know exactly how the chip can execute this command. So if you work in black box, so this kind of attacks are very time consuming. It requires a lot of time, a lot of effort to tune the parameters. I would say the setup parameters. If you, for example, using body biasing injection on the right, you can find it. It's like a needle and you touch the surface of the chip. The chip is decapped, for example, and you try to touch the silicon of the chip with a needle, and the needle is connected to a high voltage, and you can scan the needle on the surface of the chip while you are executing this kind of sensitive operations. The same if you are doing electromagnetic fault injection, so you are using an electromagnetic probe, you are doing the same, you are scanning the chip. Also the same behavior you will do using laser fault injection by focusing a laser beam on a spot on the chip. So you can imagine that this kind of attacks requires to move your probe or the needle, for example, on the XY on the surface of the silicon. Also, it requires finding the timing moment, I mean the correct timing for injecting the fault. Also, it will require other parameters like the pulse width, the intensity of the pulse related to the voltage level, for example. So there are a lot of parameters that you have to tune in order to perform, I would say, a successful evaluation, not like a successful attack, but to be sure that your evaluation has been done correctly. So the motivation is to find actually what happens in the chip and to understand how the chip can run the command, for example. And the main idea is to find the vulnerable moment of the code in order to use it for injecting faults. So this is very time consuming actually, especially if you work on a chip which is protected, I would say secure elements or this kind of protected chips. They use countermeasures, they use desynchronization countermeasures, they use power blinding techniques. So it's very important to find what we call it the timing parameters to inject faults. So that's why the need to reverse engineering tools is very, very important for us, and it will reduce actually the complexity of the design related to the timing that we spend for this kind of evaluations. So the question now, can I use deep learning for that? Can deep learning help us to automate this step to find the vulnerable moments while executing this kind of sensitive commands or not? So to answer this question, let me first show you the outline of the presentation. So I'm going to give a short introduction about how deep learning can be used in hardware security. Then I am going to move to show you how deep learning attribution methods can be used as well to detect leakage points for side channel attacks. After that, I am going to show you a practical example, which is a chip from Analog Devices. It's a secure authenticator, okay, that we have found it actually in several hardware wallets to be used as a secure chip to store private keys, I would say. And after that, I'm going to highlight how we can use deep learning attribution methods to attack this kind of black box chips, for example. And I'm going to end up with the tooling that I used and also to conclude the presentation. So how deep learning can be used in hardware security? So there are a lot of techniques that use deep learning in side channel attacks. We call it like profiling attacks. And a lot of researchers actually proved that this kind of attacks are efficient, especially if the design contains a lot of countermeasures like masking or desynchronization, for example. Also, there are some works that showed that deep learning attribution methods can be used as a leakage detection technique that can help in reverse engineering the design to understand exactly what happens while we are performing side channel attacks. A very small example. So if you would like to use deep learning to attack a chip, for example, let me stress on ES. You are running advanced encryption system, for example, on the chip. And you can change, for example, the plain text and the keys, and you try to collect more information about what happens in the chip. The information that I'm talking about in this case could be electromagnetic emissions or the power consumption during the execution of ES. And we try to build a dataset under known plain text and keys. After that, we are going to deliver the dataset that we created to a deep learning model, whatever a CNN or MLP, for example. And after that, we are going to create a model. Then we have the same chip or maybe a different chip, but it should be the same vendor, I mean the same chip, but it could be a different physical chip, I would say, under a unknown key that we don't know the key, and we repeat the same experiment, but we don't know the key. After that, we are going to use the same model that we built before, and we test it actually on a tested data set, and then the output will be like a set of probabilities. Of course, the correct key is going to give the highest probability that the model predicted. Let me give you a practical example. So, like running an ES on a 32-bit MCU, like STM32U5, you can see on the left that there is a setup that I'm using electromagnetic emissions to measure the emission of the chip during the execution of ES. On the right, you can see the signal of the electromagnetic emissions that I obtained. And I'm going to give this kind of data sets to a deep learning model under changing the plain text and the key. And after that, I will see how deep learning can help us to attack the key, for example. So I built a deep learning model based on MLP, multi-layer perception. You can see that there are only three dense layers. First layer is related to how many samples you have. We are going to give to the model. And also I'm using in the middle layer only 10 dense layer. The output layer will be related to the length of the key that you are going to attack. For example, I'm going to attack only one single byte here. So there are 256 values that could be brute forced that indicates that the probabilities of the guessed key. So after building the model, I'm going to use a test data set of a key that I don't know. And I can see that the correct key can appear after only less than 10 traces. I'm able to attack the key. So this is a practical example of how deep learning can be used to attack this kind of, I would say, crypto algorithms, which are implemented in hardware. So this was a toy example. The design doesn't contain any countermeasures to make the attack difficult, I would say. But this is, I would say, practical examples that you can start with. The second category of using or of how deep learning can be used to attack hardware devices is to use deep learning attribution methods actually as a reverse engineering tool to understand what happens in the chip. So what deep learning attribution methods? So this kind of methods are used to interpret and understand the decision of the model. For example, it can reverse engineering the decision of the deep learning to understand which pixel has the best impact on the decision of the deep learning, I would say. There are two categories. There are gradient-based methods and activation-based methods. On the right, you can see a practical example. It's related to MNIST. MNIST, it's a very well-known data set for deep learning. So it's based on images with numbers. You're giving them to a deep learning model. And at the end, you are going to give the model an image with a number, and then the model is going to predict if the number is correct or not. So on the top, on the right part, you can find that there is an input challenge, which indicates a number of 7. If you use the attribution method, the result will be like reverse engineering the decision of the model, so it will highlight which pixels are used to give the decision that this is a number 7. Okay. One of the methods, it's called activation-based methods. It's like layer-wise relevance propagation, LRP. The main idea is to calculate the relevance of each neurons in the model that you created. And the relevance is related to the activation of the neuron multiplied by the weight of the neuron. The main idea is that you are going to calculate the weight or the decision or the relevance of the neuron, and you are going to shift back this until going to the first, I would say the first layer, to know which pixel is used to interpret the decision of the deep learning model. So this is an example. You give an input challenge to 6, and the LRP result is going to show you the pixels that made the model to decide that this is already a number 6. There are other methods that you can find. It's called Tyler or input, for example. Well, I would say that it almost gives the same result. But if you are going to use this for side channel, maybe you have to brute force all the methods to find the best way on your traces. How this can be used in side channel attacks? So we have seen some works before that use this practically into side channel attacks, and they started to see that this is a very efficient tool, especially under countermeasures if the designs are protected against masking or using masking or desynchronization countermeasures, for example. A practical example based on ES also. So you can measure the power consumption during the execution of ES. And after that, you can label the data set on the S-box, I mean the output of the S-box of the first round. And then you will compare the deep learning attribution methods with the normal classical statistical tools which are used in side channel attacks like SNR, for example, signal to noise ratio. You can see that on the top, on the figure which is on the right, you can see on the top you can find the power consumption of the chip while executing the first round of ES. On the red, this is the SNR, which is related to detecting the leakage of the first round, for example, of the first byte. And in blue, you can find the LRP method. You can find that the SNR is completely equivalent to the LRP. So now you can find that this kind of techniques can behave like normal statistical tools inside channel to detect the leakage points into side channel attacks. But there is an advantage here if you are using CNNs, for example, because it's CNN, it's convolutional neural network, are based on multiplication layers that can filter this kind of countermeasures such as delay or masking, for example. So we believe that this kind of techniques are more efficient compared to statistical techniques which are used in side channel attacks like SNR or t-test, for example. To give you another toy example, so you can imagine that you have two cases that indicate that the chip is protected and the chip is unprotected, and there are two values in the power consumption trace, and whatever the value of the leakage, the value is going to give a decision that the chip is protected or not, and there is an artifact jitter in the power consumption, okay? And you are going to perform the t-test or the normal statistical tools like t-test or difference of means, for example. You can find here the t-test output is very noisy. I mean, here. It's very noisy. It cannot detect where the value is manipulated. So for you as an attacker, this is not good because you don't know where you are going to inject fault or where you are going to perform the side channel attack, okay? However, if you go to deep learning attribution methods, for example, you do the same. But here I'm going to learn from the value itself, if it's 1 or if it's 0, to indicate if the chip is protected or not. You can see that in blue, this is a sample of the trace, and in red, the value which was reversed by the deep learning attribution method. So now I'm able to know exactly where this peak is manipulated, even under countermeasure like desynchronization, for example. To show this method on fault injection, actually, it's better to show this using a practical example. So let me present you the targets that I used. It's called DS28C36. It's a secure authenticator from Analog Devices. Actually, it was designed by Maxim Integrated. It's a French company which was acquired before by Analog Devices. Okay. So it's a secure authenticator which is used for performing, I would say, security algorithms like elliptic curve encryption, and also it has a TRNG, and it has a very important feature which is called 8 kilobit EEPROM. And we started to have seen this in many products because there are some hardware wallet vendors. They started to use this kind of chips in order to store the private keys inside the EEPROM. Okay, so the main idea now, we will investigate how we can dump this memory using fault injection attacks and how deep learning can help us to do this. The data sheet of this chip is not public, so we spent some time to reverse the commands of the chip, because the chip was used in an open source hardware wallet. So this helped us a lot to reverse the commands of the chip to understand how many pages, for example, user pages in the EEPROM. So we found that there are 16 pages which are used to store user secrets, okay? And we found that there are several slots also are used for public key crypto. And there are some slots which are used to store random values and also RAM buffers, okay? We decapped the chip backside, and then we started to look on the surface of the chip by the infrared camera in order to perform laser fault injection. On the right, you can find the layout of the chip by the IR camera. Well, if you are familiar with reverse engineering hardware circuits, you will understand that the red part is related to a memory that could be the flash or the EEPROM, which is used to secure this kind of secrets. And there is the logic part here, and this is the glue. We call it the glue. And the small memory here, maybe it's related to the RAM. And there is an analog part here. And of course, this is responsible for the analog section of the chip. So we started to build the setup using a laser bench from Alphanov. And we used a scaffold board, which is a homemade tool for us that we use to communicate with the device under test and to perform this kind of commands, to send I2C commands, I would say. And there is a high-end oscilloscope to measure the power consumption of the chip while executing this kind of commands, I mean the read command of the EEPROM. The first step, of course, is to store a value in the EEPROM and in a slot in the EEPROM, and we didn't protect this slot actually, so this slot is not protected, and we started to store a value and then read this value again, just to understand exactly what happens in the chip. So to understand deeply what happens, we started to measure the power consumption while executing this kind of commands. So you can see on the top here, this is the power consumption of the chip when you read a slot, okay? This is a 256 bytes read memory, okay? So you can find that here, the chip, I mean, in zone which I give it like number 1, the chip is performing, I would say, a calculation. We don't know what is it, actually. And after that, there is an access to the memory, which is number 2. Why we thought that this is a memory access? Because there are 32 beaks that may indicate to 32 bytes access to the flash. And then there is a certain operation here. We don't know yet what is it, but we believe that this is a decryption algorithm which is used because the data should be stored encrypted inside the memory. Now the next step is to differentiate between when the slot is protected and unprotected, actually, and to compare between them to see what happens. So in red, this is the power consumption of the chip, while the same slot is protected. So we wrote data, random data to the slot. We started to read, and then we logged the slot. After that, we started to communicate with read command again to understand exactly what happened. So you can see that there is a divergence moment here. And in this moment, the chip will understand that the slot is protected and it won't reply. Okay. Now, the next step is to perform fault injection. This step is very important. And okay, now you have a power consumption trace. You have a certain window of timing to inject faults, actually. So the classical way is to try to execute the read memory command while the chip is protected and try to inject faults. Okay. So the scenario is like you prepare the fault parameters. I mean, you move the laser spot on a certain position on the chip. You do the chip restart because you may inject a fault and it crashes the chip. And after that, you start reading the page. Of course, during this, you are going to brute force all the parameters of the fault related to the level of the power of the laser, the position, the physical location on the chip, and also the offset where you are going to inject a fault here. Okay, you have a very long. This is not a very small trace, but this is I call it a very long trace to inject faults here. So you have to find the correct parameter in terms of timing where you are going to inject a fault. The first thing that we started to believe that if this chip is not protected, there should be a security bit configuration, I would say, stored in the EEPROM to give the decision if this page or this scenario actually is protected or not. So we started to focus on the EEPROM, scanning the EEPROM using a single fault. And we found that, well, we didn't find any fault. If we shoot it in the EEPROM, we obtained different chip responses. Okay, most of them that if the chip is unprotected, it replies with a reply that indicates that the slot is protected. Sometimes you crash the chip. Sometimes you get a NAC, I mean a communication error. And also we dumped two values that were not correct. I mean, it's not the same value that we stored in the slot. So to understand exactly what happens, how we dumped these two values, and the two values are indicating what exactly. So we started to monitor the power consumption. We found that the response number 3 here, maybe it's, if you find here, this is the power consumption of the chip during the response of number 3. There is a read memory execution here. So it seems that you are reading a public key slot. It's not a private key, okay? But for example, if we show the power consumption in case of 4, we don't see the read memory pattern here. So maybe this is related to RAM. So there is no access here to the EEPROM. So we expect that the response number 3, it's related to a public key value, and number 4 is related to an RNG, for example, or a RAM. Why? Because there is no any EEPROM access pattern, okay? So this was a classical scenario to inject faults. Because you work in black box, we don't understand exactly what happens in the chip. We don't understand if the chip is protected or not. Personally, I spent like 2 months scanning the overall chip, but I didn't obtain any successful fault. There should be a way to reverse engineering what happens in the chip during the execution of this command. So that's why I started to think about deep learning and to use the deep learning attribution methods that I showed before. So how this can be done? So as I told you that I started to think using this kind of techniques which are used to side channel attacks, but to use it into fault injection attacks. The main purpose for me is to reverse engineering this kind of commands because I'm working in black box and I don't know exactly where or when the security configuration bits of the EEPROM are manipulated. So more precisely, I'm going to use deep learning to locate on the power consumption trace where this kind of bits are manipulated. If I know that, it will be easy for me to inject faults. Okay. So I started to collect a data set from the chip, when the chip is protected and when the chip is unprotected. And when I call data set, this is related to the power consumption of the chip. So the main idea is that I have the chip, I have the target. I'm going to have two situations now. The first situation is related to unprotected case. The slot is unprotected, and the second situation is related to a protected case. I mean, I will lock the slot. And then I'm going to label them with two different labels, 0 and 1. And I'm going to deliver all the data set to the deep learning network. And then I'm going to test again on a test data set a value or a power consumption trace from when the chip is protected or unprotected. And after that, I will use the deep learning to reverse engineering what happens in the model to see how the model is able to learn if this value is 0 and 1. There should be, I would say, some magic values that help the model to understand if the chip is protected or not protected. So I expect that there should be some significant peaks here to show exactly where this kind of security bits or security configuration bits are manipulated. So as I told you, that I started to now collect power traces, and then I start to concatenate them together to create the data set, and then it's very important to do some signal processing if you are performing this kind of deep learning to improve the performance. So I used normalization techniques. Okay, and then I have only two labels because I'm the situation now is the chip is protected or not. So it's 0 or 1. So the guess that I have, it's only two values, 0 or 1. And then I'm going to use profiling techniques using a deep learning model to help us to understand exactly what happens in the chip. After the learning phase, I'm going to reverse engineering what happens. So I'm going to load the model to an investigation tool, okay, to perform this kind of deep learning attribution methods like gradient or LRP, for example. There are a lot of things that you can do. After that, I'm going to deliver the model a test trace, for example, and then I start to visualize the trace or the result that was taken or resulted from the attribution methods. So you can find here, there are on the top, this is the power consumption of the trace using under two cases, when the chip is protected and unprotected, but I cut the traces just before the divergence because the timing window, which is very interesting for me, just before the divergence, because the decision of the chip was taken just before, okay? And you can see in below actually the result of the deep learning attribution methods. It indicates a significant difference here. I mean, I will call it zone 1. And there is a peak here, which is before the divergence. So it seems that there are two significant differences which are separated in two different timing zones. So this means that maybe the chip is protected against single fault attacks. I mean, there should be a double verification or there should be double access from the memory. This indicates that the chip has a countermeasure, and maybe if I'm going to inject double fault attacks, the attack can succeed. So I started to scan the overall chip. To be honest, I just neglected to work on the EEPROM because now the decision should be taken in the logic, not in the EEPROM. Okay, so I started to focus on the EEPROM and trying to inject faults using laser by the knowledge that I got before from the deep learning attribution methods. I obtained a successful fault, and I showed you on the right image here. This is the position, the physical location on the chip where I obtained the fault. It's important. Okay, I already dumped the values that I stored in the EEPROM, but it's important also to prove that the power consumption of the chip is related to an EEPROM access. So you can see here that I injected two faults. Okay, the power is raised because of the impact of the laser on the chip. And you can see after injecting this kind of faults, the two successful faults, I obtained a pattern that indicates a memory access. Okay, and this was the correct values that I stored before. Okay, so this is a memory read. Okay, and after that, the chip performs a decryption to decrypt the value which are stored in the memory. Okay. Well, this is a very promising result that confirms the efficiency of using this kind of techniques into fault injection attacks. Well, as I told you, there are a lot of slots in the chip. There are several slots related to storing this kind of secure user data. And also there are 2 or 3 slots are related to elliptic curve and public key crypto. The attack didn't pass for the 3 slots of the public key crypto. I think the chip doesn't use the same scenario for this. It doesn't say the same scenario for user slots compared to elliptic curve key storage slots. So I think there is another attack path, but the attack now is applicable only on the 16 slots of the user data. Okay. Related to the tooling, so I spent some time to do a tool for using all the deep learning attacks that were implemented actually in the literature. The tool is called SCADL. The tool also integrates deep learning attribution methods, and it's an open source tool that so you can clone it and investigate. You can try it by yourself, and don't hesitate if you have any questions. We can help you. Just to conclude, if you are doing this kind of attacks in black box mode, I would say it's difficult to reverse engineering what happens in the chip. It takes a lot of time. So it's very important to use some tooling for this. In addition to classical statistical tooling, we believe that using deep learning would help a lot in this kind of evaluations. Also, vendors, they should have some guys who are more related to deep learning and machine learning methods to help in evaluating the countermeasures that they propose, because normally there is a separation phase between people who are doing countermeasure and people who are doing the test. So people who are doing the test, they are only coming from the hardware background. I would say electronics, statistical tools, that there should be people also who are, I would say, with machine learning and deep learning background to help in this kind of evaluations. Also vendors, it becomes easy now to attack designs which are protected against single fault attacks using this kind of techniques. Protecting against single fault attacks now it's not related to adding another verification to make the attack can be doable using double fault attacks. It's easy, so you have to increase this kind of number of verifications. Also, there should be other countermeasures like desynchronization countermeasures also that must be combined into the design. Also, there should be power blinding techniques, because the chip that we have seen recently, it doesn't contain any power blinding techniques. It was easy to monitor the power consumption of the chip and to see exactly what happens. Okay. Yeah, of course, this was not sufficient to reverse engineering what happens in the chip using the power consumption, but we need additional tooling. But well, we were able to investigate exactly what happens in the chip, but not in a very precise way using the power consumption. So yeah, I think I'm going to close now the presentation, and thank you very much, and don't hesitate if you have any question. Yeah. So your question is how many traces, right? Well, it depends on the design and the quality of the power consumption traces that you have. I collected 50K traces when the chip is protected and 50K traces when the chip is unprotected.
How long did it take?
Oh, it takes, to collect the traces? Depends on the oscilloscope that you are using and also the speed of the command. For me, it took like 2 hours.
2 hours? Oh, that's okay.
Yeah,
and to train the model?
Sorry?
And to train the model afterwards?
Train the model, it takes like, well, training the model, it depends how many samples you're using in the trace. But I would say, as I remember, this, every trace, it has like 20K samples. So I used them once. I didn't cut the traces or divide it into chunks. So it took like, well, I have a very poor computer. It was not, so I used my personal computer for this. We always use high performance machines, but I was able to do this on my computer in less than, I would say, 15 minutes.
Oh, that's great. Thank you.
You're welcome. Any question? Okay, thank you very much.